Okay. Thank you, everyone, for attending. The purpose of this talk is to give you some background in GPU computing and specifically how you can use OpenACC to get started with GPU and accelerated computing. If you have not done any GPU computing before or have not done any OpenACC, that's fine. We're hoping to really establish just some base knowledge to help you get started. Next slide, please, Allison. As you can see on the agenda, we're going to get started with just some basics about what I mean by accelerated computing and also what I mean by compiler directives. Then we're going to walk through a process that I use when using OpenACC to accelerate a program. And then finally, I want to leave you with some next steps of how you can begin using this knowledge to apply OpenACC to your application. So getting started, what do I mean by accelerated computing? On most machines that you purchase now, whether it be your laptop, your supercomputer, or even your cell phone, typically you'll find two different types of processors within that device. You have what we call a traditional CPU, central processing unit, which is really highly tuned for serial performance. So if you think about a small number of threads or even just one thread that operates at a very fast speed. And so in CPUs, you'll typically have say a half dozen or so high-speed cores around a very high clock speed. And these have very large caches that help keep the data close to those fast cores so that they can operate quickly on a single-threaded performance. But typically you also have a GPU, and GPUs are really tuned for what we know as data parallelism. So if you think about hundreds, thousands, tens of thousands, hundreds of thousands of individual elements that need to be computed, and these can be computed independently of each other. GPUs are very well tuned for that. So the way you achieve high performance on GPUs, which typically have a lower clock speed, typically have smaller caches, is through parallelism. And we use parallelism to hide the latencies to memory, to instead operate on many thousands of elements all at once. And the thing to note about accelerated computing is that we don't want to force you to use one or the other of these processors, but really to use both of them together and to use the CPUs for their strength, which is high serial performance, and use GPUs for the bulk of your program where you have high amounts of data parallelism. And there are several programming models that you can use to do this, and they really range in simplicity and performance. Accelerated libraries are an approach that we really like to push you towards. These are things like what we call our cuBLAs, our cuSolver libraries, cuFFT. These are common math routines that we've already written high-speed libraries for you. So in many cases, you can actually, without even changing your code at all, take advantage of these libraries and get very high performance. And what's really nice about accelerated libraries is someone else has already done the hard work for you. So you don't actually have to write this hand-tuned code for any particular architecture. You can simply rely on the fact that we at NVIDIA or your other vendors will always provide you with the best possible library for using with your code. But unfortunately, you are limited by what libraries are available. And so while if you're doing a lot of, say, dense linear algebra or sparse linear algebra, FFTs, random number generation, many of these operations are common enough that you'll find a lot of libraries available to you. But as soon as you start to get out of those domains, typically you'll find that there aren't accelerated libraries to do what you need. The next step up in simplicity is compiler directives. Compiler directives are at a very high level, so they're based on the existing programming languages you already use, C, C++, and Fortran in the case of OpenACC. So you can stick with the language that's familiar to you, and you can add these directives to your code in order to accelerate your application. So the goal is for them to be simple to use and feel familiar because you're still writing your code in a way that you're used to writing it. The trade-off is because they are so high level, frequently the performance is not optimal. Usually you can get upwards of 80% of hand-tuned performance, but if you really want to get the absolute best possible performance, that you'll need to move to a lower level. For most users, the ability to rapidly accelerate large parts of their application and get good speed up often outweighs that trade-off. But if you really do need to get the absolute best possible performance in a part of your code, then we do also offer parallel language extensions. And so in the case of an NVIDIA platform, this is where CUDA falls. So CUDA exposes very low-level details of the architecture to allow you to really tweak your code for maximum possible performance. You can really optimize your code for the particular GPU where you want to run. Of course, these extensions are often a little more difficult to learn and frequently more time-consuming to implement than compiler directives. And so we really want to teach you that using compiler directives is a great starting point for accelerating your code. And really, these three programming models don't need to be exclusive. They can all coexist within one application. So what we really encourage you to do is start off with libraries, because you can accelerate your code in many cases without even changing a single line of source code. We really encourage you to implement as much as possible using these libraries. You can always count on, by using standard libraries, that you can move your code forward in time, and know that we will always provide you with the best tuned performance for new GPUs as they come out. And when libraries don't have what you need, then we encourage you to look at compiler directives, specifically OpenACC, to rapidly accelerate your code. So take important parts of your code, accelerate them with directives, and get more and more of your code accelerated quickly. And once you've accelerated as much of your code as possible using directives, if there are certain parts of your code where you really they're really performance critical, you really need to get the best possible performance, well, then you can actually use programming language such as CUDA along with these directives to get best performance in those isolated parts. And by using all of these together, you really can accelerate your code very quickly, and you can also develop code that is highly portable. So if you develop something in the programming languages such as CUDA for speed, you could know that on other platforms you still have a directives-based version you can use as well. So we really encourage you to take this tiered approach, starting with libraries, moving to directives, and using programming languages at the very end to get the absolute best possible performance in isolated parts as a way to work very productively and very portably. So I keep using this term compiler directives, but I haven't actually defined them yet. So compiler directives are a way to accelerate your code that you add this information to your existing code. So if we see here on the left, I have this loop, actually this nest of loops inside of my code, and I've added to that an ACC parallel loop. And so this is the first directive that informs the compiler, here is a region of code where there is parallelism, and I want you to build that for the GPU. Take your existing code, add additional information using directives in Fortran or pragmas in C and C++, and the compiler will do a lot of the heavy work of figuring out how to parallelize that code, what data needs to be moved to the GPU, and all of that is handled for you by the compiler. So what you could then do is add these to your code and then incrementally optimize your code beyond that. And one thing to note is that compiler directives are always ignorable. So if you have a compiler that doesn't understand this language, they'll be ignored. Or if you have a platform where the compiler can do better things, the compiler can take that information and do better things for you. So here we're taking a CPU code and we're accelerating it to a GPU, but this just as easily could have been another form of accelerator as well. OpenACC is the specification that we're going to use to teach you today. OpenACC is designed to be simple as a way to accelerate compute-intensive applications. It is an open specification, so it's designed by a committee of members and released in the open so that anybody can implement it. And so we really want it to be adopted in as many places as possible. And it's designed to be portable, so we try to represent the parallelism at a high enough level that it's not specific to an NVIDIA GPU or a CPU or even a particular generation of hardware, but we represent things at a high enough level that as new hardware comes out, the compiler can map that parallelism to that hardware for you without you having to think about the differences between architectures. So we really aim to be performance portable across any type of architecture. On this slide, you can see that it does have a fair number of members and supporters, and so it really is gaining in support. Now, for the rest of this presentation, I want to walk you through the process that I take when accelerating applications. And so we're going to use a case study here to do that. The process I advocate is really a four-step cycle. First, we need to identify the parallelism in your code, and that could be using any tool that you're already familiar with to understand the performance of your code. So understand where the time is being spent in your code, what are the important hotspots, and looking in those routines to find out, is there parallelism in this routine that I'm not using? Next, we're going to use OpenACC to parallelize the loops in the parts that we've identified. So we find where the time is being spent, and we then use OpenACC to parallelize within those routines. We'll do that a lot. We'll introduce a lot of parallelism to the code, and frequently what happens is code actually does slow down at this point. And that's because with the GPU and the CPU being two distinct memory domains, we're moving a lot of data between the CPU and the GPU that may be done in a way that's not optimal. So the next step is to optimize the data movement in our code, or what we call data locality. And finally, once that step is done, then the last step is to optimize the performance of your individual loops. And for most users, by the time they get through the first three steps, they've already accelerated their code to the point that this last step is only a few percentage, if anything, that they'll gain. And so we really encourage you to work on these first three steps, and then the last step is just for the last few percentage of performance. So for this case study, I'm going to use a fairly simple code that's known as a Jacobi iteration. This is a code that works in an iterative sense to try to find one correct value. By looking at the values of my neighbors, I can calculate what my next value will be. So this is a very common algorithm that's used in a lot of scientific domains. So you can see down here I have a square with 5 points. This gray point in the middle will figure out its next value as the mean of its neighboring values. And that's what all this formula down here tells us. And so here's what the code actually looks like. You can see we have an outer while loop. That is our convergence loop. So it's going to continue to iterate until one of two things happen. Either we get to an answer that we consider close enough, and so that's what this error tolerance is. So we figure out what is the maximum change that we've done across all of our array elements, and if that change is below our tolerance, we're going to say that we found a good answer. Or the other condition is we don't want to iterate beyond some maximum number of iterations. And for all of the performance graphs I'll show, we fix that so it always runs for 1,000 iterations, just to make sure it's a fair comparison. This next loop nest here goes across all of the matrix elements. They then calculate their new value based off the current value of their neighbors. We figure out our convergence error, so that's what we're looking at here, the difference between our new value and our old value, and we find that maximum error. And then the lower loop nest is swapping our arrays. So we take our next value and we load it into the A array. And yes, in a more optimized sense, some people would use pointer manipulation here. That's always pointed out to me that you could swap pointers here. But for the case of simplicity here, we're doing it in this way. So that's our algorithm. So step one is we're going to identify the parallelism available to us in this code. And so because this is such a simple code, I don't need to use any performance profiling tools, although in a real application you probably would go through and profile your code and find where the hotspot is. Here I've already identified that this loop is the hotspot. And so let's look first at the while loop. Can the while loop be parallelized? And it turns out it can't. And that's because for every single iteration of this loop, it relies on the data calculated in the previous step. And so there's always this dependency between iterations. So that means we can't parallelize this loop. However, for these inner loop nests, the thing to note is that for every single I by j element of A, we're calculating independently. So these can be run forwards, backwards, in any order, and it can be run in parallel, and we'll still get the same answer. And the same is true for that bottom loop, of course, that all we're doing is copying from one array to the next, and so these iterations are independent. So what we found here is that these nested for loops inside our iteration are parallelism that we're not exploiting. The next step is going to be to use OpenACC to parallelize these loops. This is what an OpenACC directive looks like. You've already seen one example of this earlier. In C or C++, we use pragmas. So pound pragma, ACC is the sentinel saying, I'm going to speak in the OpenACC language. And then we give a directive and some clauses. And clauses are just additional information to that directive. And typically in C and C++, you would place this before a block of code. So a block of code might be a loop, or it might be just a set of curly braces to identify a region of code. In Fortran, instead of a pragma, we use a specially formatted comment. So bang $ACC. That again, that denotes that the rest of this line is an OpenACC directive. We give again the directive name and the clauses. And in Fortran, because there aren't these structured code blocks, frequently what you'll find is there's a matching end directive. One thing that is important to point out is a lot of people, when they first get started, they'll leave off that ACC. So they might say pragma parallel. And in fact, that ACC is very important because it tells the compiler that the rest of this line is OpenACC code, so it knows how to understand it. So the first directive I want to introduce you is the parallel loop directive. And it's actually two directives that are merged together. The parallel directive identifies a block of code that contains parallelism. And the compiler is going to look at that block of code, and it's going to generate what we call a compute kernel, where a kernel is a function that runs in parallel on the GPU. If you've done any CUDA programming, this term will be familiar to you. If you have not, then that's simply the meaning is the kernel is what we launch and run on the GPU. And lastly, the loop directive identifies that this is the loop that I want to be parallelized. So if I simply say parallel, the code is going to be launched on the GPU but run redundantly. By saying loop, it identifies that this is a loop that I want you to parallelize. And frequently these are placed together as you see below. So pragma ACC parallel loop. So I'm saying here is a for loop that has n iterations, and I want you to parallelize that loop. And what it's going to generate is a kernel where every thread on the device is going to calculate one element of y based off of x and y, and that would be our kernel. So if we apply this to our code, you can see we've identified two loops as parallel, and so I've added two parallel loop pragmas to the code. The first one, of course, in the first loop nest, and the second below. Now, one subtlety here is this reduction clause. And this is something that if you've not done any parallel programming before, you might not be familiar with. A reduction is saying that there are n by n different values for this error variable. And every single loop iteration is going to calculate its own value for error. But at the end, I only really want one. I want the maximum. So I'm going to reduce the n times m different values of error down to the one absolute maximum across all of them. And so I need to specify that to the compiler. Many compilers will figure that out for themselves, but the best thing to do is always to expose this and ensure that the compiler understands that there is a reduction here on the error value. That's what that's saying here. All I've done is added 2 lines of code to this, and I'm going to compile it. Now I'm going to choose to use the PGI compiler. There are multiple OpenACC compilers available, but the PGI compiler is the most widely available on a lot of different targets, a lot of different platforms, including Linux and Macintosh. And so you can see here I have my pgcc command. The -fast is my optimization flag. So think of this like O2 or O3 on other compilers. -fast is a good optimization level. And see what I've added here is this -ACC, which enables OpenACC support, and -target accelerator Tesla. So I'm building for an NVIDIA Tesla GPU. The other thing to note here is I've added this -minfo flag, and that's telling the compiler, inform me what you've done to the code. And that's what prints out all of these extra lines down below. And the 2 that I've highlighted in green are the most important ones right now. That is telling me that on line 55 and line 66, which is where I've added those pragmas, it's generated an accelerator kernel. So I know it's looked at my code and it's generated code for the device. The other thing it's done is it's actually looked at understanding what data is needed on the GPU, and it is created device copies of that data, and all of that is handled for me automatically. So down a little lower, you can see what we say, generating a copy out and generating a copy in. I need to copy A to the device, and I need to copy A new out from the device, and that's what it's showing here. So all of that has been figured out for me just by adding those 2 lines of code. Now it turns out OpenACC does have a second approach that some users find a little simpler. I like to teach parallel loop first because it's very descriptive. I understand that this loop should be parallelized. But now that you understand what a kernel is, I'll tell you about the kernel's directive. And the kernel's directive identifies a block of code where I believe there may be parallelism, but I want the compiler to find it for me. And so here I've got 2 different loops. I've got an initialization loop and a calculation loop down below. And I've wrapped all of those in an ACC kernel's directive. The compiler is going to analyze that, and if it can determine that the first for loop is safe to parallelize, which it is, it will generate a GPU kernel for that. And if it determines the second one is safe to parallelize, which again it is, it will parallelize that. And so here I've now been able to accelerate more of my code using this one directive. The trade-off is that, of course, I'm relying on the compiler to be able to correctly interpret my code. And so in this case, it's very simple, and the compiler can do that. So looking again at our Laplace code, you can see I could do the same thing with adding this ACC kernels within my, my iteration loop. And it's important to note, a lot of people, when they encounter this example in the wild, and we do have this example in some of our labs that we give at GTC, people will try to put this ACC kernels around the while loop and say, this whole function I want you to try to find parallelism. And if you do that, it's probably not going to work, because the compiler will encounter that loop. It'll realize that that loop is not parallel, and it probably won't go any further into that loop to find parallelism. So it's really important where you place this in your code. You need to understand where in your code there may be parallelism and point that to the compiler, and then allow the compiler to parallelize it. So again, showing you the compiler output from this, you can see that the compiler, once again, was able to identify 2 accelerator kernels for us with that one directive, and it also was able to identify this reduction that I talked about previously. So it figured out for me that a reduction needed to occur. So you might ask why there are 2 different approaches and which approach you should take. The parallel loop approach requires more analysis by you. You as the programmer need to look at your code, make sure it's safe to parallelize, and then mark each individual loop where it is safe to run to run in parallel. So if you've done this analysis, then you can ensure that the compiler is not going to miss this. If you identify this loop as a parallel loop, the compiler is going to generate parallel code. The kernels really relies on the compiler to perform the parallel analysis, and it will do what it believes is safe. The compiler can't afford to be wrong, and so if it thinks it might not be safe to parallelize the loop, it's going to skip that loop. And so one of the things you can do is if you start with kernels, sometimes parallel loop is something you can fall back to force the compiler to recognize that this is a place you want to accelerate. What's really nice about kernels is if you've not done any parallel programming before, it's much simpler because the compiler is doing the analysis, and it also allows you to cover more of your code all at once. So the final thing I'll note is if you've done any OpenMP programming and have OpenMP in your code, the parallel loop is going to be a very familiar approach for you. If you've done no parallel programming at all, the kernel's directive may be a more straightforward path for you. But really, you will need to determine for yourself which approach feels more comfortable to you. Both of them work equally well, and you can really get equal performance from both. It's really a matter of preference in your situation. So what happened? We built this code, we ran this code, and you can see as I increase the number of threads, this code does speed up with an increasing number of threads. It doesn't perfectly scale because of just the characteristics of the code. But one of the things to notice here, and I'm showing speed up, so higher is better, that the OpenACC code actually slowed down. And it's time to dig in to figure out why, because frequently when you first get started accelerating your code, you're covering huge amounts of your code and letting the compiler do a lot of work for you. And then you, as the programmer, has to come back and give the compiler more information about the code to get good performance. So here you can see I've slowed down by about 15%. All right, so in order to do that, I'm going to pull out a tool that we ship with CUDA, and that is the Visual Profiler. If any machine that has CUDA installed will have the Visual Profiler, and it will work with OpenACC codes. So I ran it through the Visual Profiler, and I've clicked through a couple steps here to cut straight to the punchline. The Visual Profiler tells me that I have very low compute to mem copy efficiency. And so what that means is, if you compare the time I spend computing on my matrix and doing the hard work versus the time I'm spending copying data between the CPU and GPU back and forth, I'm spending way more time copying data. In fact, you can see here I'm spending about 5 seconds computing and over a minute copying back and forth. So let's look at our code and see what's going on. So here I've zoomed in a lot on the code. Here's my convergence loop, and here's just that first loop. And you'll notice here when I come into the convergence loop, both of my arrays, A and A new, are on the host, on the CPU side of the machine. And I need them on the GPU, so they get copied automatically to the GPU by the compiler. So now I move them over to the accelerator. I compute on them, and then when I get back to the bottom, they're on the accelerator, and the compiler thinks, hey, we're going to need them on the host, so it copies them back. And this happens over and over again every single time we iterate on this loop. And again, the reason the compiler does this is it can't afford to be wrong. It always has to be cautious. It always has to ensure that if there's any chance the data is going to be needed, that it's going to be copied back to the device. So let's evaluate whether the compiler made the right decision in that case. So zooming back out, here is my loop. And you can see here I have my upper ACC parallel loop and my lower one. And between those loops, it's doing a data copy. Well, does the CPU really need the data between those loops? And it turns out no. There's actually no code on the CPU between those loops. And so we know as the programmer that data is not going to be needed again on the host at that point. Looking again at the bottom of the second loop nest, what we can see is that the very next time that this data is going to be used is going to be the next time around the loop. And so what we can tell as the programmer is that I don't actually need to copy the data there. I need to copy the data at the end of my convergence loop. After I've found my final answer, that's when I need to copy the data back. And that's the knowledge that the compiler doesn't understand. And so we need to go through and inform the compiler of this. For that step, we call optimizing data locality. Data locality means once something is local to the GPU, it remains on the GPU as long as it's needed until it's needed back on the CPU, or what OpenACC calls the host. So to do that, we're going to use the OpenACC data region. And the data directive, it defines a region of code where we want to share our data. And so you can see here if I just add an ACC data region here, and notice I've had to add some curly braces to identify a block of code here. In Fortran, you would do an ACC data and an ACC end data at the bottom. But within that region, any arrays that are used are going to be shared. And just that is an important optimization. But we're going to go a step further because we know more about how this code works. So we're going to use data clauses. I mentioned that directives also have clauses to give additional information. In this case, we have these data clauses to give additional information to the compiler about how to copy the data. So skipping the first one for a second, a copy in is a case of I want to copy this array from the host to the GPU device. And a copy out is the other direction. I want to copy from the GPU to the CPU. A copy is both directions. It's a copy in at the beginning and a copy out at the end. A create says any arrays I have listed here in the create clause, I don't need to actually copy the data back and forth, but I do need to ensure there's space on the GPU for them. And the last one is present, which we don't actually need in this example, but what that specifies is somewhere above this function, I've already moved the data, so you can assume that it's already present. And then there's some additional clauses here that will soon be unnecessary with OpenACC 2.5, but we have a present or copy, which says if it's already present on the device, use it, and if it's not, then copy in or copy out or create. In OpenACC 2.5, that just becomes the default behavior, and so that will just those clauses actually go away. And that 2.5 is coming out later this year. Now, in addition to specifying here are the arrays that I want you to copy, frequently, especially in C and C++, you'll need to specify the size of those arrays. So if you think about the compiler may not understand how big an array is because you've allocated it using malloc. So frequently you need to explicitly give a shape to your array. So you can see here on my first one, the C and C++ pragma, I have a copy in of A, and I'm saying start at 0, because that's where C arrays always start at 0, and copy size elements, where size is the number of array elements, not the size in bytes. And you can also specify a part of the array. So you can see on B, just for this example, we're showing a particular section of the array, and that does need to be a contiguous section of the array. Fortran, usually if you're copying the entire array, because Fortran arrays are self-describing, you can simply say copy A. But if you wanted to give more information, then you could say here start at 1 and copy until element end. So it's slightly different because of the language differences here. This is the starting and ending value for Fortran, where it's the starting and the count in C. But again, in Fortran, you can also specify a portion of the array. And these clauses can appear on data regions that I've already shown you. They can appear on parallel regions as well, and also kernels regions. So we're going to apply this to our code. So you can see here, I've outside of my my while loop, I've added a data region. So that's identifying for the whole extent of that while loop. I want the data to remain on the device. And I've given it some additional information. I've identified the fact that I need the input value of A, and I need the final value of A. So I'm going to copy A in and out. But with the A new array, the values are meaningless except in here. It's basically temporary. So here I have create A new. Allocate space, but don't do any data copies. This is knowledge that I have about the program that I've now given the compiler. And looking at the compiler output, you can see that it now says, instead of generating a copy in of A and a copy out of A new, you can see it's now respecting what I've told it. And if we look at the visual profile of performance, I've now zoomed in a huge amount from the last picture, and you can see I'm showing 2 iterations of loop, and notice there's no data movement happening between them. There are some slivers for that error value, but otherwise there's no data being moved. And you can see I've reduced the time per iteration from 104 milliseconds, as it was when I was copying the data in and out at every step, down to just 4.8 milliseconds. So it makes an enormous difference. And looking at the overall performance, you can see now we've gone from a net loss to a net gain, where we've increased the performance about 6x over a single CPU socket. And so that's the frequent workflow here, is that we'll accelerate as much as possible, and in doing so slow the code down, and then optimize our data motion away and speed the code back up to where it should be. Now I do want to show you, just because here I'm working on a very simple code where all of the data exists within one function, or all of the code exists within one function. That's not typically the case in real codes, and so I want to make sure you understand that when you go back and start applying this to your application, some of the additional steps you might take. And for that, I mentioned the present clause. So typically in an application, you don't have everything in main. You have main calls into some functions, or calls into other functions, and typically you'll span all the way up and down that call tree. And so as you develop with OpenACC, the goal is to identify the data motion as high as possible, to leave the data on the GPU as long as possible, and then use that data inside of your functions. So here I've restructured the code where I have a main that calls into a function called Laplace2D, and that Laplace2D is what we've been seeing all along. Inside of main now, I've handled copying A to and from the device. So if there were other functions within this data region, they can reuse that copy of A. And then inside of my function call where I'm doing the work, you can see I've marked A as being present on the device. So that's specifying you, the compiler, can assume that I've already moved the data there elsewhere. And I've also specified here to create a new. So as you develop your code, frequently it'll take a very bottom-up approach. We'll accelerate the loops at the bottom, and then we're going to move our data higher and higher up the call tree in order to get good performance. And that's a very common approach when using OpenACC. And I mentioned that the last step is to optimize loop performance. And it turns out that this particular code is so simple for the compiler that there's really nothing further to optimize. And so I've actually called out this step in a separate presentation. If you go to gputechconf.com and you search for this talk I've highlighted here, that's another talk on advanced techniques that I gave at GTC. So I encourage you, if you're interested in caring further with optimizations, that you go back and watch that talk. So I do want to leave you with some last steps before I open things up for questions. And I want to remind you first of how we accelerate using OpenACC. First, we need to look at the code, analyze the code, and understand what are the important parts of the code and how much parallelism is there. You keep in mind that GPUs thrive on many thousands of independent operations. So you want to find loops, or more often than not, loop nests where you have many thousands of independent operations. So once you've identified where in your code you have that pattern, then we parallelize the loops using OpenACC. And I can't encourage you enough to express as much of that parallelism right up front. Go ahead and don't be concerned if your code begins to slow down because of data motion. Put as much on the code as possible, put as much on the GPU as possible, and make sure that you're getting correct results. Do this just incrementally adding more and more loops. And once you have a significant amount of your code on the device, then begin to optimize the data motion using the data directive. You, the compiler, always know best when the data is going to be needed, and so you need to give this knowledge to the compiler. And the reason I have those in this order, and the reason I say put as much on the device as possible, is it can be very error-prone if you're adding a loop, putting a data region, and then adding another loop, and then moving your data region. It's simpler to go ahead and accelerate as much of your code in a bottom-up manner, and then do the data motion on the very last. And I find personally that that's less error-prone. And then the last step is to optimize the loop performance, and put that absolute last, because until you've optimized away the data locality, you really can't tell which of your loops need optimization. You saw earlier I had 5 seconds of compute and over a minute of data motion. So it was really, there's no good way for me to determine how much a change I would get by optimizing my loop until I've gotten rid of the data motion. So always save that step to last. And here's the typical experience we have. So we have our baseline where we've identified our parallelism, and we begin adding our parallel directives. We begin slowing down the code. We begin optimizing data locality, and you can see here that's when our curve speeds up. And then the very last step is to optimize loops where we get the last few percentage points. This is a very typical exercise, and I really want to drive that home because many people who really started with OpenACC got frustrated with this step 2 and forgot to move on to step 3, and it's really important. And this is not a long-term process. With OpenACC, this is an hours or days sort of process rather than a many months process. So really being able to work through each of these steps very quickly helps you to accelerate your code. Finally, to leave you with some last steps here, check out openacc.org for more information about OpenACC. There is a programming guide that's in process that will be added there shortly in the coming months, and that's something that documentation will hopefully help even more. There are several tutorials that are available on demand at gputechconf.com. Some of them were given by me, and some of them were given by users and other colleagues. So really, you can get a lot of good information there. Once you've used OpenACC and had some successes, I do want to plug that there is a workshop in November at Supercomputing called the Workshop for Accelerated Programming Using Directives. And there's more information. I encourage you, once you have some success stories, to come share them. And lastly, we have a service called Quick Lab, and I encourage you to take a self-paced lab there. And Julia is actually—
Okay, great. All right. Let's go to the top of the questions that began when you started presenting. We had a question regarding do OpenACC compilers have support for ARM, such as the NVIDIA Jetson TK1?
So not at this time. The PGI compiler did demonstrate some support for ARM at Supercomputing last November, and so you can see that there is some development in that direction, but the current releases do not support OpenACC on ARM. I would encourage you to look on pgroup.com, that's the PGI website, and contact them to find out more information. I'm not sure, since I'm not within that group, what the current plan is, but definitely try to contact them and find out what the plan is for that.
While using accelerated libraries, for example, cuSparse, can we include CUDA code as well?
So absolutely. One of the things I like to point out with those three approaches is all three of them can exist in the same application. You can use something like cuSparse, you can use CUDA and OpenACC all within your code. And what I really like to do in my codes is use OpenACC to handle the data management, so I can have just the one representation of data and let OpenACC handle the device and host copies, and you can pass that data into cuSparse, and you can likewise pass that data into CUDA. So you can fully mix all three approaches. If you'll search on the Parallel for All blog, which is our developer blog at NVIDIA, there's an article I wrote nearly a year ago demonstrating how you can mix OpenACC with libraries and with CUDA, and I actually have some examples associated with that are available on GitHub, so you can see how to mix the different approaches together.
Will OpenACC and OpenMP merge into one standard?
So we're working really hard on that. I'm actually a member of both committees, and we're working very hard on trying to bring them closer together. OpenACC, being a smaller and more focused organization, really moves a lot faster on accelerators, whereas OpenMP has a broader scope and has to move more slowly. And so we're working on trying to bring them together. There are similar features available, and trying to bring them as close as we can, so that eventually we can really try to have just one language and one specification. For the foreseeable future, there's going to be two, just because the two are driving together. And if you use OpenACC, I do want to point out that any restructuring you do to get more parallelism in your code, to identify data motion, all of that is just as important. You would be doing the same work in OpenMP as well. So we really are trying to bring them together, but I do want you to know that using one does not mean you can't use the other as well. That you're doing the same work, and it's just a matter of syntax to try to use them both.
Question just came in as you were answering that. Which compilers support OpenACC? PGI-CC, NVIC?
So currently, PGI compiler is the most widely available. There's also the Cray compiler, if you happen to have access to a Cray. GCC is in the process of implementing, so they have preliminary support in 5.0, and 5.1 is expected to have full support for OpenACC 2. And then there's several research compilers out there as well that are also working on this. And for example, OpenUH, OpenARC, there's several research compilers. But as far as production level compilers today, it's primarily PGI and Cray, and then GCC is the up-and-comer that's really beginning to expand support.
Regarding the Pragma ACC parallel loop, what if there are more loop iterations than the maximum number of threads?
That's not a problem. The compiler will understand that the limitations of your hardware, and so all you've done is expose the parallelism. It's up to the compiler to determine how to use that. So if a compiler looks at this and says, well, I have 1 billion iterations, and on this device can't support 1 billion independent threads, then it will build your code in a way to either strip mine it or somehow map the parallelism down to the hardware level. So that's something that you as the programmer don't have to think about, that the compiler will use its knowledge of the hardware and the information you provided in order to build the code. So that's one way that OpenACC is very powerful, is it's abstracted away those low-level details from you.
On your slides 21 and I believe also on 24, the question is, why are there both implicit and explicit array notations in your optimization report?
That was on 21.
21, and I think then again on 24 it was mentioned.
Okay, so in this case, well, all we've done is we've introduced parallelism directives, so either parallel loop or kernels. So the compiler has to look at this and understand that we have a CPU and a GPU with two distinct memories. And so it's going to analyze the code for you and find what data is actually used within this region of code and ensure that there's not only space on the GPU for it, but that we copy the data to ensure correctness. So this is really a case of we're trying to represent things at a high enough level that you as the programmer don't have to think about this. The data movement is only an optimization, and that you will be able to ensure that you'll get correct results running on a distinct memory device. Or if you happen to be running on a device that has unified memory, the same thing would be true, that the compiler would understand that and ensure that you get this. The reason we also, in addition to that, have explicit is, as I demonstrated here, that there's times where the compiler, because it must ensure it gives correctness, is going to be overly cautious. And you as the programmer can identify the fact that something like, in the case of our example here, the A new array, the values of that are meaningless on the CPU and are never used outside of this region. And it's difficult for the compiler to know that. So by also having the explicit data management routines, it allows you to give that knowledge to the compiler.
So on that same note, I believe the question coming in was trying to understand how to locate the code that's being sent to the GPUs, and if that code is always only within loops. Can it be independent?
Can it be independent? So what I think the user may be asking is, if I have this region of code that I want to run on the device, and I have another region of code that's completely independent, can I run them concurrently? I think that might be what they're asking, and that's an advanced feature that I talk about in the GTC talk I referenced. But yes, so OpenACC has a feature called asynchronous queues. So there's an async clause that you can add to your directives, and what that specifies is put this code in the CUDA stream number 0, for instance, and put this other code in stream number 1. And because our hardware supports running those concurrently, it will overlap those appropriately. If that didn't answer the question, please put a follow-up in the chat.
There's a question regarding, I'm curious to know how this technology compares to C++ AMP.
Okay. So they have very similar goals. So C++ AMP and OpenACC and Thrust in C++ and a lot of these other technologies are really aimed at representing parallelism at a very high level. So you don't have to worry about the nitty-gritty of how to map the hardware to the code, or wrap the code to the hardware, but rather do these things at a high enough level that it will be portable. So very similar goals. Syntactically, they're fairly different. So C++ AMP is an extension to C++. If I remember correctly, it's proposed by Microsoft. I'm not certain of that. Is an extension of the C++ language for parallelism that's not available in C++ by itself. Similarly, something like OpenACC, something like OpenMP are extensions layered on top of C, C++, and Fortran to add additional parallelism. So similar goals, syntactically different, and I think for many users, it will come down to personal preference of which meets your coding style better. For Fortran and C programmers, OpenACC fits very well. For some C++ programmers, their coding style is more better addressed using something like Thrust, but OpenACC is also available to that.
Can OpenACC be used in Visual Studio?
That's actually an excellent question, and I don't believe it can. PGI is available on Windows, and I think it does have some Visual Studio integration, but I'm not certain how deeply that works. And so I think that would be a good question to ask on the PGI forums: is how well their OpenACC compiler works with Visual Studio. I typically run on Linux platforms, so I'm just not as comfortable with that. So I think you should probably ask on the PGI forums. If it works well with Visual Studio, it would be through the PGI compiler. And so check on the pgroup.com and on their forums.
General question: how difficult would it be to transfer the entire application to GPU? Would it be just writing a wrapper to enable this, or would you have to make different routines?
So it's really difficult without seeing your application to be able to guess. But the goal with OpenACC is that to identify where are the really parallel loop nests. So in many applications that may find that there's 4 or 5 functions where you need to add pragmas to the function and accelerate those loops. In some routines, it may actually be as simple as adding the routines or the pragmas at one place in main, and it will work. So it's really difficult to say without seeing your application and understanding better where the parallelism is and things like that.
Can OpenACC use multiple GPUs?
Absolutely. I have an example in the referenced GTC talk. Let me go back to the end so you can write down that number if you need. Where we take a simple code and we tile it up and break it across GPUs. The way it's done is very similar to CUDA. You would call a function saying, from here on, use this device, and then any pragmas that you have or any directives you had will go to device 0, for instance, and then you call the function again and say, now I want to use device 1, and any pragmas will be sent there. So check out the talk referenced here, the Advanced OpenACC Programming talk, and I do have an example there where you can use it with multiple GPUs.
Okay. One of our attendees would like to know how data is transferred to the GPU. Is it an asynchronous transfer? Are streams used to overlap operations?
That's a great question. So by default, it is a synchronous operation. However, you can make it asynchronous. So again, in this exact same talk, we have an example where we break up our computation and we can make it asynchronous. That way we can copy individual chunks of data and overlap them with the computation. So by default, everything happens synchronously, but by adding the async clause, the OpenACC async clause, you can make it asynchronous and begin overlapping with other operations.
Great. Let's see, we have probably time for 1 or 2 more questions. I will go to, are there any plans for OpenMP or OpenACC for cache optimization and data locality? For example, loop, filing, roll, and jam, etc.
That's a great question. So OpenACC has what's known as the cache directive, and that is specifically designed for finding small parts of the code or small parts of your arrays that can be cached within your loops, and in most cases this would, on our platform, go into shared memory. Now that directive has actually turned out to be fairly challenging to implement, and it's only really recently, within the past, say, 6 months or so, that the compilers have begun to really be able to exploit that very well. Additionally, there is a tile directive that is designed exactly as you're describing here, where you can tile your loops because there is a particular 2D locality, for instance, within your loop. That directive exists, and again, is only now beginning to be really well exploited by the compilers. I have actually discussed something like unrolling as well, and that may or may not come in the future as a possible optimization. But I would say to check out on openacc.org to read up on both the tile and the cache directives, and then if you have specific examples, if you can post them online on Stack Exchange or something like that, and we may be able to help you either show you how to apply those directives to your code, or if we don't fit your need, then it'll really help us with improving the specification. So so there is some support, but it's really not as mature as some of the other features.
Okay, well, we had a couple other questions, but I think for now those covered really the top ones, and I will also send the questions to you, Jeff, so if you want to respond via an email to some of them, that can also occur. But for today, let's call this a wrap. I want to thank everybody for attending, and I want to thank you, Jeff, for presenting. Also, just to let everybody who's still on the line repeat to know again that we are sending a link to the recording as well as a link to the PDF of these slides that Jeff presented, and that will come to you via email shortly after the conclusion of this webinar. We'll also, for all those who attended live, give you the information that Julia went over regarding Quick Labs as well as the program that she mentioned. So thank you again, everybody, and I look forward to seeing you at our next GTC Express webinar. Bye.